Quick recap on what is the conditions for equilibrium. We looked at this in the previous video. We're going to focus also more on static equilibrium instead of dynamic equilibrium, because static equilibrium means at rest, no net force, no net torque. Dynamic is if it's moving without acceleration. Anyway, first one, no resultant force. Remember what that is? Means all the horizontal forces should have to be zero. Means all the forces to the left equals to all the forces to the right. The other one, vertical forces should also add up to be zero. This is F sum of Fy. So everything going up, all the forces equals to all the forces pulling down. Which also means, because force is zero, then about acceleration. Net force zero means acceleration should also be zero in both the x and the y direction. Okay. One quick mention is you can also use, because all these forces are vectors, right? If you don't want to break into xy, xy, you can also think of it in terms of vector diagrams. So let's say you have three forces and you arrange them tip to tail. So one, how to draw? 1, 2, and 3. If they form a closed triangle, like this, means it is in equilibrium. Tip to tail, no net force. But what if you have something else like this? 1, 2, and then 3. Uh-oh. So now you have some net force, the purple one. So this one is not in equilibrium. How about torque? So torque, basically you want to say no resultant torque, so the net torque is 0. In other words, all the clockwise moments equals to anti-clockwise moments. If you want to think of it in the graphical sense, you can think of line of actions. Let's say you have, just give me a moment to sketch out. This is similar to what we did in the previous one. If you have three forces, let's say 1, 2, and 3, and you trace that their line of actions intercept at a point, if you can find this point, we call it a pivot point, you can find a pivot point where there's no net torque, this object is in equilibrium. So this is using line of action of each forces to track and check whether it's in equilibrium or not. Okay, so today we'll be looking at a lot of rods, horizontal rods and slanted rods. Let's go. First one, we got a street lamp fixed to a wall by a metal rod and a cable. Which vector triangle could represent the forces acting at P? Take a look at the picture. Let's draw out some forces, shall we? First, you have a tension holding up the rod and the lamp. Okay. The lamp has some weight. Okay. The rod, if you want to draw, also has some weight. That's it. Any other forces that we're missing? The rod's not merging into the wall, right? Something's keeping the rod up, out of the wall. Contact force, reaction force. So there's one that kind of looks something like that. Let's call it R. Note that it may not always be vertical. Sometimes we'll see in later example it may be up, sometimes it may be down. But for this question, we're going to look at P only. So on P, there are what stuff going on there? Let's draw a free body diagram for P. Has the weight of the lamp pulling it down, tension and an angle, and an R to the right. Weight of the rod doesn't affect. Okay, let's see the choices. Ooh, it's in triangles. So let's look at the weight first, the vertical one. Weight can't be up, so these two are out. Weight down, weight down. Okay, correct. Tension, so tension, tension. And R, R. See which one's wrong? Tension's in the wrong direction for one of these. Tension should be pulling up, so in this case, D is the answer you want to choose. Let's look at more calculation type with the horizontal bar to better understand it. This one is a paper 2 question on page 39 if you want to do that as well. More than welcome to pause the video and try out some things first before I discuss it. Okay, rod is kept horizontal and in equilibrium. Ring the bell, conditions for equilibrium. Okay, the wire provides a force to hold up the whole thing. So let's label it 44 newtons. 44 newton. They're asking what is the vertical component of F and horizontal of F. Unfortunately, they don't use the letter T because T or tangent. Anyway, horizontal and vertical. So we have, let's redraw it. There's an F of 44. You're going to have a vertical component, Fy. You're going to have a horizontal component, Fx. You can also draw the other side lah, same thing, but you will use a different angle. Because if you use this bottom side, that's 30 degrees. If you use the top side, you have to think of 60 degrees. Choose whichever one you want, 60 or 30, and solve. So A1, vertical component, Fy. I'm going to use a 30, feel free to use the other one. But 30 will be opposite hypotenuse, so I need to use 44 sine 30. Equals to, okay, I'm going to use my calculator later. Then Fx will be 44 adjacent hypotenuse, so cos 30. So use calculator and calculate, you should get about 22 newtons for the vertical component. And this one has a lot of decimals. I usually just write everything out so I can see them, and then round them off to 3SF, 3 significant figures. So there we go, vertical and horizontal component. So you got 1 mark each. So first is just an A1, and then another A1 mark. Okay, that's part A. Let's look at the other parts. Part B. By taking moments about the P, where is P? P, determine the weight of the rod. Think of moments. Okay, so we need to choose a pivot point. They kind of chose for us already. Take moments about P. So they're telling us use this P as your pivot point. Nice. Okay, what are the forces is going to cause clockwise, anti-clockwise torque? We'll write them down later. But firstly, this rod is in equilibrium. So you can say your net torque or is 0. Or you can say the clockwise moments equals to the anti-clockwise moments. Okay. Clockwise moments, what do we have? Just W times, how far is it from P? 0.64 equals to anti-clockwise. Oh, what is the anti-clockwise moment? Don't panic. Just now we found F has a vertical component of 22 Newton. This is Fy. We also found F has a horizontal component of 38.1 Newton. 38.1 is acting on the pivot, so no use lah, no effect. But the Fy has an effect, so it is 22 newtons times, how far away is it? 0.64 point 0.9. That is about 1.6 meters for the whole thing. So then you can find your W, and this is for part B. Okay, let's calculate. 22 times 1.6 divided by 0.64. 55 newtons. If you got 55 newtons for your weight, that is correct. First mark comes from you knowing how to calculate moments. So C marks are basically equation marks. They see, oh, you know how to do torque equals force times distance. Can already lah. Okay, then you got your final answer correct. That's A1. For A for accuracy. Okay, part B. Oh, sorry, part C. Come on, part C. Okay, explain why the wall must exert a force on the rod at P. Now, please don't use the unofficial term. If you use my phrasing and say, oh, because the rod doesn't sink into the wall. That is the unofficial term for it. You want to use something more solid, some reasoning backed up by some maths. So, this is how we can talk about it in part C. Firstly, why do we even need a force there? Okay, yes, it touches the rod. Wall touch rod, so got reaction force. But how to think of it in terms of equilibrium? You see, all the horizontal forces add up together should be 0. What are the horizontal forces in this picture? Only got 38.1. No. So force to the left is 38.1. So there should be some force going to the right. There's also 38.1, but there's no force. Oh, so we're missing out some kind of force here. How about vertical? All the vertical forces should be 0. Going down, we have weight, we found just now, 55. And going up, go up only got 22. Oh. So we are missing some force. Actually, I should say, yeah, some mysterious force is missing to make the whole system balance. So this mysterious force actually is the force at P, which we should give a name later. Yeah. Let's call it force at P. So the wall does exert a force that has to help balance out the whole system. So how you can explain this in a sentence, there are many ways to do it. I'll just list out all the points, how you can do this. You can say the tension in the wire, F, has an unbalanced horizontal force. So unbalanced horizontal force of, how much is it? You can also write down. That is 38.1 Newton left. So it's unbalanced, so it will need some other force from the wall to help push that out. Another way is you can talk of the vertical. How you can do it is you say the vertical part of this wire, Fy, which is only 22 newtons, is not large enough. To do what? Not large enough to balance the weight, which is 55 Newton. So some other force is needed there. Lastly, this one is talking about the graphical method. You want to draw graph. You can say F from the wire and W from the weight do not form a closed triangle. What that means is, if you draw them together, like F is here, weight is down. Like that only? It's not a closed triangle. So you need something else to balance out the whole system to form a triangle. That's where part D comes in. Draw an arrow to represent the force at P. Label this force S. Okay, label it as an S. So at P, there's going to be a few components, right? You have to balance out the horizontal force of 38.1. So this P, there's a horizontal part, Px of 38.1 to the right. It also has to give some vertical force. So some vertical force, which has to be what is missing? 22 plus something equals 55, right? So 55 minus 22 should be, this here should be 33 Newton. So there should be a vertical 33 Newton up. If you combine both together, you can find the magnitude of this S force, but looks like to go to the right and up, so this will be your reaction force from the wall, pushing the rod up and to the right. So as long as you got it kind of up and to the right in that sense, they'll give you a B1 mark for this thing. What I forgot to say, this one also B1 mark. If you have any of these ideas in your writing, that's a B1. So let's remember, you have a reaction force at the hinge. In this case, it happens to be upwards, pointing upwards like that. Okay, let's look at another example of slanted rods. Oh, wait, it's not slanted rod, it's still the trapdoor. Haha. Oh, look at this case. Do you see how this one is different from the previous one? First, the reaction force is going down. Ooh. What changed? Tension and weight. They swap positions. If you scroll back to the previous question, the tension was at the end. Weight was here. So now, the reaction force has changed direction. Instead of pointing up like that, it points down. So the question is, which list shows the forces in increasing order of magnitude? Increasing means increasing law from left to right. Left is small, right is big. Okay, there's a cheating way, but I'll pause the cheating way and show you how to the other way first. Okay, so let's see. Tension and weight and H. Let's break them all into components. Weight is fully vertical. Sorry, not WX, WY, fully vertical. Tension has two components, TY and TX. H has also two components, HY, HX, until here. Let's compare T and W first. So the tension, TY is already bigger than W and H together. So you can say TY is already bigger than WY and HY. Individually lah. So in that sense, you can say T is definitely bigger than W, and you can say T is bigger than H. Okay, that's just like comparing the vertical parts. Then you compare T and H specifically. How do T and H relate? They have the same horizontal component. TX, HX is the same. What's different is they're vertical. Oh, so we know for sure T is bigger than H. Because, side note, TX is same as HX. One is to the left, one is to the right. Because no other horizontal force, so these two must somehow cancel out each other. So T is bigger than W, T is bigger than H. Let's check the answers. T bigger than W means this is out, this is out. T bigger than H means D is out. So all that's left is C. Now the cheating way. Cheating way is they didn't say the diagram is not drawn to scale. So what you can do is you take a ruler and you literally measure. How long is this? How long is this? How long is this? And compare. W shorter, so followed by H, followed by T. That's how you can do it. You can only use this if they didn't say, oh, diagram is not drawn to scale. You can assume it's drawn to scale, otherwise. Okay, so this is how you can think about trapdoor hinges and reaction forces. Now we finally have the slanted rod question. I forgot there was one more before that. So this one is on page 19 if you want to try it out on a piece of paper as well. Or you can just pause the video. Actually, no, pause the video, take a look, try to see how to make sense of this question and where is the direction of the force at X. So something to highlight, equilibrium, and this thing, the diagram shows the direction, not the magnitude of forces. What this not the magnitude means, basically, your diagram is not to scale. So don't just look at the arrow and compare. It's just a warning lah. They let you know. Okay, so we can think of this in a few ways. You can think in net force, net torque, but in this case, it's a little easier to think of net torque. So let's see. Here, see, do I have a ruler? Easier to do if I got a ruler. Okay, so let's say I have a ruler, some weight here at this end. I don't think I have a weight to hang for you. Oh, I do. Wait, carabiner. Can go in, Hey, cannot. Fine, never mind. So we have a ruler, weight pulling down against the wall, and then some support like this. So you can try this out in your own ruler. Imagine your hand is the wall, and your thumb is that Z thing to hold it up like this. Okay, so you see, holding up the thing. Now if I pull down the tip, what's going to happen? How is the wall going to support this rotation? Okay, you can choose to take a moment about each point. if you take a moment about Z, how about that? Let's choose Z as our pivot, just to check and see. So then R has no effect. So if you choose Z as your pivot, W has a clockwise moment. It's going to cause the thing to move that way. X then have to cause an anti-clockwise moment here. So you know X should be somewhere below this rod lah. It should be pointing somewhere there. So that's the first clue. Okay, I'll rub it off. So it should be somewhere here, 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 here. All these directions will cause an anti-clockwise moment. Means A is out, B possible, C is definitely out. Okay. So how do we know whether it's B or D in this case? One choice they say is either here or here. Well, you need to check the moments of the whole thing. So I would say this one is not, this one is. So D is the closest answer you can choose to decide where this wall will be pushing. Why not B? Because the wall will have two components, like what we did in the previous question. Something out, it's these red color are components, and something either up or down, in this case a little bit down. So it cannot be B, because B means you have something down, these are the components, and something left. Why would the wall exert a force leftwards? It's supposed to push out on the rod, so it's to the right. So D is the best choice you can do in this case for the direction of the rod at X. Okay, so that's the whole series about rods. Hopefully this is a good kickstarter to help you think about how to make sense of rods, hinges, trapdoors, and things like that.